Today we're going to study the electromagnetic spectrum. So the electromagnetic spectrum is a bunch of waves. These waves have different frequencies, and these waves are electromagnetic waves. We means made with the electric field and magnetic field. They are not like masses that move with certain velocity, because the mass also have a wave. For example, the electron travel in a wave. But these electromagnetic waves are made of electric field and magnetic field. Like, for example, light, like the green light, blue light. These are electromagnetic waves. X-rays, gamma rays, infrared, radio waves. These are all electromagnetic waves. So we have a big range of them. So we start with we go from small. This is the small wavelength, so I put here small lambda. The lambda is the wavelength. Here is the wave, for example, and here is the wavelength. This is lambda, the wavelength. If you want to measure a wavelength different way, you go from peak to peak. This is also lambda. So this is also wavelength. So we go from the big lambda to small lambda. So the waves that are very small in this region, we cannot see. The waves that are very big, we cannot see. We see only certain range. We see from 400, I put here 400 nanometer to 700 nanometer. These are the wavelengths that we can see. We can see in this range. For example, the green is somewhere here. This is the green light. Is here somewhere in between. And here this is the violet. And the blue comes before it. And here we have the red. So this is the red. That's the violet. So we see this region here, this red region. Okay. Now, these nanometers, 1 nanometer is 10 to minus 9 meter. So this wave here that have this length from 400 to 700, we can see. For example, the sun gives radiation. It doesn't just give electromagnetic radiation, it gives other radiations, because particles, heavy particles, they also come out of it. Like, for example, electrons, they move with a high velocity, and then you have other particles that come from the sun. Now, some particles have mass, some don't. For example, the electromagnetic radiation, which is just photon, doesn't have mass. Okay. So if we start from this 700, go to 400, in this region here, we have the ultraviolet light. So this kind of radiation is high energy compared to this, because the wavelength is short. The wavelength is short, so it's high energy. You should know that the energy of the electromagnetic radiation, I put here, energy of some radiation is equal to Planck constant. This is Planck constant. H is equal to 6.63 times 10 to minus 34 joule second. And the frequency, H times the frequency. F is just frequency of that light. So that's the energy. the frequency of light, it depends on the period. So I put here 1 over the period. And lambda, the wavelength, is equal to the speed of light times the period. So lambda, which is the wavelength, is equal to c over the frequency. So the frequency of light is equal to c, speed of light, over lambda. The speed of light is just 3 times 10 to 8 meters per second. Now we take this frequency here, and then we put it there, and we get the energy. So the energy is equal to h times this c over lambda. Now look at this equation here. This h is fixed, c is fixed, lambda is variable. So if the wavelength is short, the energy is high. If the wavelength is big, the energy is low. So this group here have small wavelength. Look, for example, here I put gamma radiation or gamma rays. Gamma, put here gamma rays. So these gamma rays have very short wavelength, so they have very high energy. So gamma rays are very high energy waves. They can actually penetrate concrete, several feet in concrete, gamma rays. And between this ultraviolet and gamma rays comes this group X-rays. So these are also high energy. So the X-rays have small wavelengths, so they have high frequency, so they have high energy. That's why when you go to the dentist, sometimes they make you wear some heavy vest made of lead so that X-rays won't penetrate or won't go into the rest of your body. It will go just to your jaw instead of your heart or lungs. So it's high energy radiation. So it's in this region here. So to the right of this red interval, you have just the high energy radiation. Now if we go to the other, well, I didn't mention here I didn't mention the wavelength. For example, the ultraviolet here, you can have like lambda 10 to minus 8 meter. Okay? 10 to minus 8 meter for the wavelength. For the X-rays, you can say 10 to minus 10, the average. 10 to minus 10 meters, X-rays. For the gamma rays, we can say 10 to minus 15 meters. 10 to minus 15 is a Fermi. 10 to minus 15 is a Fermi. 1 Fermi is equal to 10 to minus 15 meters. So look at the wavelength, it's really very short. So the really high energy radiation. If we go to the left side, here we have the infrared. Infrared. So now we're going in the direction where the wavelength is getting bigger. So infrared don't have as much high energy as in the spectrum. So these are bigger wavelength. So the energy is going to be small. Look, if the wavelength is big, the energy is small. So the average, I would say 10 to minus 4 meters. Okay. Now if we go, we have also if we go back here, we have the radio wave. We can, in this region here, radio waves. So, for example, the AM and FM signals belongs to this group of radio waves. So the radio wave, I would say lambda, approximately 10 meters, average radio wave. But remember, you have big range. It's big range here. Now, here we have the long wave. They're long waves. They can go up to, for example, 10 to 8 meters. So these are long waves. What is 10 to 8 meters? 10 to 8 is 10 to 5 kilometer. That's 100,000 kilometer. Because I have 10 to 8, so 10 to 5 kilometers, 10 to 3. So I get 5 zeros, 10 to 5. Now, the radius of the Earth is about 6,400 kilometers. This is the radius of Earth, approximately 6,000. Look at here. This is 100,000 kilometers. So that's really, some waves are bigger than the radius of the Earth, or bigger than the diameter of the Earth. So these waves, they go with the speed of light. Why? Because they don't have mass. No mass, you go with the speed of light. If you, for example, take some particle, like some rock, we have a rock here. This is a rock. Now, this rock, when you look at it, it's sitting still, sitting on the table still. Now, it looks still. Remember, there is a temperature in that room where the table is. Here is the table. There is temperature. If actually you try to see that rock with kind of very sensitive instruments, you're going to find that the rock vibrates. The reason it vibrates is because there is temperature. So the temperature, if you have something that vibrates, it means it has temperature. For if it doesn't vibrate at all, temperature is 0. I'm talking about 0 Kelvin. Okay? Now, if you make this rock small, then it starts to vibrate more. Okay? Because if you increase the temperature, this will vibrate more. Now, if the particle is even very small, teeny tiny, it starts to move faster because the mass is decreasing. Okay? Now, in the room, you have heavy particles, they go slow. Small particles, they go fast. Now, if you go to like an electron, then it starts moving very fast. And then, remember, the mass is decreasing here. I'm starting from the rock going down, so the mass is decreasing. So here the electron will go really very fast with a high velocity. And now if you take that electron and take off the mass, you have now a particle with no mass. Then it will go with the speed of light. Okay? So as the mass decreases, the particle velocity increases. So these electromagnetic waves, they don't have mass. So we go with the speed of light. So these radiation, they don't need a medium to travel. It's not like sound. Sound need air to travel, needs a medium. But the electromagnetic radiation, it travels in a vacuum. If you have empty space with no energy, with no mass, no medium, the electromagnetic wave will travel in that space with they don't need medium to travel. Okay?